While we get started, I'll talk about myself and introduce the fantastic guest we have with you here today. My name is Monica. I'm a developer advocate here at Starburst, and I am so excited to talk to Adrian Estala, our Vice President and Field CDO, and then also Daniel Abadi, PhD, Computer Science Professor at the University of Maryland, College Park, and also an O'Reilly book author, which is the whole purpose of this conversation. Is we are here today to discuss the new book called Data Virtualization in the Cloud Era. So let's give them a small round of applause just before we get started, and then we'll jump right in. Awesome. So let's just kick off a little bit of the discussion. Daniel, can you just level set with us what is data virtualization?
Sure, yeah. So data virtualization, what it is that, let's say you have data in different places. You have your HR data in this database, and you have your finance data in this database. You have 5 different applications running and all on different databases, or maybe some of them in the same database. And you just have data all over the place. And now you want to access your data. So what you would usually do is if you need HR data, you would go and you would go to the place where HR database is, and you would interact with it there. Or if you need finance data, you would go there. Or if you need this app, you go there. And so you go to the specific place where your data is, where you want to access that particular data set. So that's fine. The basic problem, though, is that if you have lots of different sources of data and different places where data is stored, then you have to kind of learn how to interact with each and every different system. And that can get a little bit complicated. It can get a little bit sort of high effort in order to be able to learn all the different languages and all the different interactions and APIs, all the different places where your data is stored. So the basic goal of data virtualization in general is to have sort of a layer above all of your different data sources that sort of prevents the impression, the interface that really is just one place. It's as if all your data is in one place, and you issue your requests, whether it's writing or reading that data, to that one location. And then that location then goes at that centralized data virtualization platform takes those requests and then sends them to associate places. If it's a query, it brings them in and queries them. If it's a write request, it sends it down to where they're located. And it does all the complexities, all the interactions with individual systems by its sort of on the fly without you having to know about it. So you as a user only have to understand how to interact with this one tool, and then the complexities of interacting with different tools is all done via this one layer. That's the basic idea of data virtualization.
Absolutely. And data virtualization is something that has been around for a while, but it's not necessarily something that we've seen in this era as of today. Adrian, could you kind of talk to us a little bit about today's modern data architecture and some of the new challenges that exist with results of having to tackle data virtualization?
Absolutely. So first, to the thousands in attendance and the millions around the world watching live, welcome to the show. I think we're just getting people come in. So you'll hear a difference when we're talking. I'm not as smart as Daniel. So Daniel's going to give you a very technical, very deep description. And I'm going to do my best more with a CDO lens to kind of give you a business perspective or more of a data leader's perspective. And so what's interesting about that data challenge question is that I know as a first-time CDO 6 years and change ago, I went around all my business leaders, met with finance, HR, risk, IT, and I was trying to figure out what my problem statement was. And that problem statement was, I need access to the right data for the right people fast. I need access to the right data for the right people fast. And you fast forward to today, that's the same problem, right? We're still trying to solve that same problem, trying to get access to the right people fast. I think the challenge is different only because there's much greater urgency. 6 years ago, 7 years ago, looking at my data architecture, and somebody would introduce this concept of, because there's always going to be a new architecture. There's always going to be a modern architecture. And back then, it was cloud for us. We're moving everything to the cloud. But the reality is we don't have the time. We certainly don't have the budget to redesign our architectures today. So when somebody says modern architecture, as a data leader, I think, oh gosh, I hear migration. I'm already feeling the pain. And I'm more than anything, I've got to sit in front of a business leader and say, give me some time. And nobody has time. And so I think the new challenge for that same problem statement is finding a way to do it much, much quicker. And I think with virtualization, with the new ability to address virtualization, the new approaches that we have, I think we're cracking that challenge in a different way. And we'll get into it more in the description here.
So your description there of fast data access sounds like what Daniel mentioned as what data virtualization can do. But we know that data virtualization has some negative connotations from some potential past transgressions. Can you kind of level set for us, Daniel, and talk about maybe the reason for that bad reputation?
Sure. You use the word transgression. It's an interesting word. It's not really necessarily all the fault of the software itself that existed in the past. But let's get into that a little bit. There's some theory and there's some practice with why data virtualization in general has sort of disappointed people in the past. And to some degree today, still, there's still some challenges that exist. So let's do the theory first, then we'll do some practice as well. So in theory, I don't know if it's really theory, but the basic issue, as we all know, actually a good example of this is, say, we all use the cloud. We all use Amazon or Google or Microsoft Cloud. And so we all know that in general, the way the cloud works is that you pay for what you use. Your computing, you pay for computing. For your storage, you pay for storage, and so on. And everything, basically, the costs you pay are generally somewhat proportional to what you use. There's one exception in the cloud, and we all know what it is. It is data egress, right? So data egress is priced enormously high relative to anything else. And so why is that? So the reason is that the cloud vendors don't want you to extract data out of their platform, out of their cloud, and move it somewhere else. It's sort of they want your whole applications, your whole focus, everything to be inside their cloud. So that's the cloud. That's not so relevant to us, but it's the same thing in the database vendors as well. So the Oracles of the world, the IBM DB2s, the Microsofts of the world, they all have database products, and they don't want they don't want data to be extracted out of the system and brought somewhere else. In general, that's just sort of, it's not in their interest. They want you to manage your data and to access it, to change it all within their own local platform. So as a result, they did not make it very easy to extract data out of the system. So the main way to do this, if you want to extract data out of the system into the virtualization layer, is you would use something like an ODBC or JDBC interface to query data and extract it out into the virtualization platform. JDBC and ODBC, they're very slow, right? So basically, they work at a tuple at a time, a row at a time in the database, and sort of it's just it's very often a bottleneck of the data extraction process and the query process after the extraction as well. So we have in the book, later on in the book, like around chapter 5 or so, we have some benchmarks showing exactly how slow this is. We stored some data, we ran TPCH, which is a well-known benchmark used in academia and in industry to sort of measure the performance of systems. And we took this benchmark consists of around 8 tables or so. And we stored the different tables in different locations. One of them was in Oracle, one of them was in Postgres, one of them was in MySQL, and ClickHouse, just different systems. And then we ran the queries, which access usually often more than one table, and therefore they required extracting data out of those systems and into the external layer to perform those joins and to run the queries. And those queries were surprisingly slow when they were going across more than one system. And the reason was because they were extracting them out via JDBC interface. JDBC, that was the bottleneck. Almost every single query, except for query 1 and query 6, almost every other query in TPCH was bottlenecked by that particular data extraction cost via JDBC. And that's just sort of, it could be fast. There's no fundamental reason why it has to be this way. But the database vendors they were not interested. They don't make it easy for you to extract data in bulk out of the system. So you have to play tricks. You have to do data validation. You have to sort of do partitioning. There's things you can do to make things a little bit faster, but it's very hard. And then this is why sort of historically from the turn of the century, a little bit before that even as well, we had vendors which were selling data virtualization platforms. And the way they worked was they would either they would extract data out of the system and perform it in the virtualization layer, or they push data down. And both of them have issues. If they were pulling it out, the issue was that they were sort of hitting the JDBC bottleneck, and if they're pushing it down, there are other issues. I think we'll get to later, so maybe we won't get into that too much detail now. But that was sort of that's one issue. It's a more sort of like it's just like the market forces are not designed to benefit the idea of taking data out of underlying systems and bring it into a data virtualization platform. So that's part of the reason why they failed in the past. Another reason, a more practical reason, is that the reason why we have data virtualization in the first place is that we want to make it easy for our users. We want to be able to sort of avoid our users from having to speak the language of every system they're dealing with. We'd rather have it all in this one system. The problem is that that is hard. That's what we want to automate that. But even if you automate it, you still have to have the system itself, the virtualization layer, to be able to speak the language of these systems. And these systems are constantly changing, right? So the API is not constant and different. Each system, although many systems speak SQL, it's kind of a universal language for dealing with data. But Oracle's version of SQL is a little bit different than Postgres is, which is a little bit different than MySQL. They all have different flavors of the interface. And so having the virtualization layer be able to speak the language of all these systems, especially when it's pushing data down, pushing queries and access down to the system, is also a big challenge. So that's another issue. And then the other big issue that came up is query optimization. So it's well-known sort of in the database field, which is where I work. Query optimization is one of the most complex parts of the database system. Essentially, what the idea is that the user issues a query, and then this optimizer, this code, the query itself is expressed in a declarative fashion, and the query the optimizer takes this declarative query and decides what is the optimal way to run this query over the data set that I have. So I mean, in general, it's hard because it's just sort of like when you have joins and things, the space of potential options to check becomes exponential, and it's just almost the search space of what to check to see what's the optimal plan is just too big. You have to prune it, you have to do different things, and it gets fairly complicated on a single system. But now, if you're dealing with a data virtualization platform, now you have this layer which has to understand if I do this plan, how is this system going to do it, and how is other systems going to do it. So it has to be able to reason about the costs of systems external to it. How do they do this query or how do they do that query? And that's also very hard as well. So for those three reasons, and other ones too, but those are the three main reasons that really sort of held the idea, the goal, the promise of data virtualization back. So although we had vendors for years now, for 20, 30 years, we've had vendors. My advisor, actually, my PhD advisor, Mike Stonebreaker, he had a company in the space. But many, there's many companies that existed, and they've all sort of done disappointingly. They've either the company itself did badly, or the customers felt bad because they just didn't really work. It's sort of you weren't able to really get what you could out of all the underlying systems. And that's the main issue behind the history of data virtualization, I would say.
And one thing you mentioned a couple of times is the database systems not being able to, the ODBC, JDBC connections not being able to pull that information out. And I think with the cloud, we have the ability to kind of change those underlying systems. So Adrian, I was wondering if you could elaborate a little bit about how the separation of storage and compute that comes with the cloud has actually kind of enabled this new era of data virtualization, or what you're seeing in the field.
Let me say that push versus pull section in your book was probably my favorite part. And I know you don't have enough time today to walk through that, but pick up the book, just turn to that chapter. I like the way that you describe the balance and the need for both. So I wanted to say that real quick. I think it's a really key piece. So compute versus storage, right? The separation. So I'm going to give you a non-technical answer, and what it means to me maybe as a data leader, or what it means for business teams that are trying to be successful. So the challenge that we face, all of us, I think, and most of us, I would say, there's maybe one person in the room that might say, I have all my data in one cloud. Most of us have data in multiple clouds and on-premise solutions. Most of us are dealing with data maybe in other countries as well. And so I've got data in different countries. I've got data on different solutions. I've got data in different clouds. That complexity forces us to rethink how we do compute. If I'm trying to do compute differently in every system, there's no consistency. Now I've got to train a lot of different people to do a compute a lot of different ways. From a business perspective, there's no agility in that. There's no speed in that. All I hear is cost and pain. If I can separate compute and I can treat all those systems as just storage, or better yet, I can put all that data in my lowest cost storage. Maybe I'm using lakes and S3 buckets, so to speak, object storage, instead of very expensive proprietary warehouses. But first you leverage what you have and you do the compute somewhere else. All of a sudden, you create incredible consistency. Now everybody can start to do it the same way. Now I can start to enable my business teams to understand what I'm doing, because I can teach them one way to do it. They can learn it, and they start to care and really worry about where the data came from. I don't care if it's on a lake or a warehouse or what it's on. I know how to do compute. That's the game changer to me. That it's really more about, certainly there's cost efficiency, certainly there's performance, but for me it's the agility and the speed that it affords my business that's the most important.
And one thing sort of adding to that agility is the data lake. And in the book, in chapter 2, Daniel, you mentioned that many of the most successful deployments of data virtualization in this cloud era have that underlying data lake system. So I was wondering if you can expand on that and sort of how the data lake is contributing to data virtualization in the new age?
Sure. Yeah. So I think one thing that really changed in the last couple decades or so is that we had this this emergence of these very big tech companies like Facebook, now Meta, whatever, Twitter, these sort of so these big Google, of course, these big companies that just have huge petabytes and petabytes of data stored locally. And so so what happened was around 20 years ago, I would say, is that it used to be before 20 years ago, what happened is that almost every company, that data was stored in a DBMS, in a database management system, like an Oracle or DB2 or a SQL Server. And that's really where the value was. But what happened was that the database vendors, they would charge by the space, the byte is how much, that's how they would charge the vendors. And so the big companies, the Facebooks, the Googles of the world, it was not feasible for them to even imagine paying Oracle or anybody else to store the data for them. It's just never going to happen. So they all build their own internal, sort of data stores based on MySQL or based on MapReduce, which became Hadoop. And what happened was a lot of these projects became open source, or versions of them became open source, Hadoop being the most obvious example, where it became possible for people to sort of store a massive amount of data without paying Oracle, without paying anybody else to store it for them. And the database, and the softwares worked, and there were some issues with them, but basically they worked. So the data lake concept emerged out of that, out of that era in the last 20 years or so, where now it became sort of much more popular to not store your data in a database management system, rather store it in Parquet files or Avro files, in a open source data lake software solution that sort of had no market incentive to prevent you from extracting data out of the system. So as before we said, one of the big issues with data virtualization was extraction of data was just too expensive, DBC is too slow. But if you have your data stored in S3 files or in Parquet files in a data lake, there's no, you don't use DBC for that. You can get the data in bulk directly out of those files in structured format without going through any sort of independent sort of separate sort of software to make that process slow. So that really allowed for bulk export of data into a separate system, such as a data virtualization system on the fly at query time. So that was, if you combine that with the emergence of fast networks, where we can actually extract data very fast from the underlying storage solutions, you end up being in a situation where now one of the big impediments, the things holding the vision of data virtualization back has now gone away. And now we can actually get data fast out of those underlying systems. So what we see today is that when you use data virtualization today, you may still have some data in Oracle and some data in other places as well. But you have also some data in Hadoop and some data in S3 files. And at least those data, and those are usually your big data sets, those ones you can get directly much faster. So one of the big performance issues has sort of gone away when you have your bigger data sets in these sort of more open solutions.
And then that satisfies Adrian's business side of getting data fast and being able to, have and see the results that justifying it to your business cost. And so I think we're at the place where I want to talk through push versus pull data virtualization. And I know we've mentioned it in the past, but Daniel, I want to really just dive in there. Can you tell us the difference and kind of the architectural components of each?
Sure. Yeah. So it used to be the old way to do things in the data federation world and the data virtualization world was basically the push-based model was the main way to do things. Because it was so expensive to pull, since it was just so slow to get data out, what they used to do is sort of a query would come into the data virtualization platform or the software. It would take the query and they would divide it into pieces. It would say, okay, well, this piece of the query needs to be sent over here because the data source for this part of the query is over here. This part of the query is over here, so I'll push this part down too. And then it'll just sort of do the final combination of results in the data virtualization layer. Most of the work was being done in the underlying systems. So it was sort of doing complex SQL analysis and SQL sort of partitioning to sort of divide the query into parts and then push down those parts to the underlying systems. So that's how things used to work. And the main problem with that architecture was that was what we said before, is that sort of you would then the platform would have to speak the language of every other underlying system. You have to know not only sort of how to get data out of the system, but also how to sort of express queries over that system. All the details, all the different things. How are dates managed? How is times managed? How do I deal with this particular user-defined function? Those things are sort of specific to each system. They're different. So it was very hard for the data virtualization layer to be able to generate these partitions of queries to send them correctly in the correct language to underlying systems. Plus, then optimization, probably mentioned before, also get that in spades now because it's doing most of the work in underlying systems. So you really have to know the cost. What is it going to cost me as far as time, as far as resources to run this query? So it was very hard. And what was really hard about it wasn't just the initial version of the software, but then the code maintenance was enormous because now every time they change something in the API, now you sort of rewrite the entire sort of virtualization layer to sort of handle this change in the API underlying system. So that was also a big issue that really made things sort of much harder. And then there was still some amount of extraction out of the systems which was slow and joining, which get a little bit complicated. So that was the way things used to work, and it never really worked. So almost every company that did push-based data virtualization, they almost all failed or disappointed to some degree. It was really hard to get right. So what's really changed in the last decade or so is that now most data virtualization solutions now use a pull-based model, where rather than pushing queries down, they pull data out, and they do most of the work in the data virtualization platform itself. And so this is made possible by the existence of data lakes and the bulk export, which is faster now, by fast networks as well. But the key thing this does that sort of saves you is that instead of, you don't have to speak so much about, you don't have to know so many details about underlying systems. Now you only need to speak just sort of like, how do I get data out? What is, basically, how do I want to select star, or with maybe some basic filters, but the language for getting data in bulk out is usually much simpler than the details of specific types of queries that we head down to the system. So if you're pulling data out, pulling out in bulk the raw data, that tends to be much easier, and it requires less knowledge of the specifics of the underlying system. Furthermore, the optimization now, since most of the work is done in the data virtualization layer, then the optimizer has to focus just on that. It doesn't have to reason about the cost of the underlying system as well. So that process is much simpler to build, and therefore more likely to be successful. It's just, just in practice, building complex systems is hard, and it usually fails, and building simple systems are more likely to succeed. So because this process is simpler, it really kind of works better. And it wasn't even possible before because we couldn't pull data out in bulk fast enough. But now we can, and that really sort of flipped the equation and really makes things possible now. It wasn't possible before.
That's awesome. I'm glad that it's now possible. And so we've talked a lot about sort of the theory behind this new data virtualization cloud layer, and I want to transition into some of the case studies that are shared in the book. And some of the main themes that were found in the book, you and your colleagues analyze a lot of some actual implementations of data virtualization. And these implementations have, multi-instance, hybrid data virtualization systems. And there was a lot of themes that were discovered in these case studies. And, some of these themes were accessing data, some themes of abstraction, and decentralized data ownership, being the main challenges that people are still facing and the things that they're trying to solve. So, Adrian, I was hoping that you could talk to us through some of the, practical applications of data virtualization, specifically talking about that decentralized data ownership piece and maybe the data access piece.
Yeah, absolutely. Andy Mott, your co-author, who isn't here, I love to hear him talk about this idea of new data and new questions. That's the competitive advantage, right? So it's most of us have probably solved, or we have a way that works for answering old questions with old data. I know the data, I know the questions, I built a model, let's run. The competitive advantage for us now is trying to figure out how to solve new questions faster with new data, and data we haven't explored yet. I bring this up because I think we think about a practical implementation. One massively practical and useful implementation is to use this approach for discoverability. I like to build these discovery labs or discovery domains where you bring business teams in to ask new questions, and you allow them the ability with a virtualization layer to connect to a lot of different sources. I don't care what cloud it's on. I don't care if it's on-prem. I don't care where it is. It's a secure environment. We're just mining for data, looking for data. What if I bring this table and this field and this table and I join it this way? Will that work? No. What if I do this? And so the ability to allow them to ask questions on new data and then ideate. It's one thing when you ask a question and IT goes away for 6 weeks and comes back with an answer. You forget why you asked the question. When you give the business the ability to ask a question and ask another question and ask another question, and you're in the room discovering new data sets, it's powerful, right? And I think that's a very practical, immediate win for virtualization today. The other one I would say, we talk about big business cases. There's so many different patterns to this solution. There's patient 360, there's veteran 360, I've done finance 360, digital twin, if you're in energy, is a similar solution. But when we start trying to find ways to bring a lot of different data sets to support a big business process, like a supply chain process, for example, or a healthcare process, you can't do that without this approach. There's no way you're going to be able, because of compliance, because of cost, and because of speed, you're never going to be able to get all that data in one place. And so you have to use a virtualization layer to connect to all those different data sources. And if you're dealing with data in other countries, forget it, right? You need to be able to do the processing, the compute in that country, and then manage exactly what's coming across. And this is where we start thinking about things like data products. We haven't talked about data products yet, and I'll talk for another hour about data products. But in a virtualization layer, if we think about simplifying that for the consumer, you're not going to create a virtualization layer and then tell your business teams, there's all the data. You might do that in the first phase of a discovery exercise, but what you're really trying to get to is you're trying to say, here's a virtualization layer filled with rich data products that are described, that are ready to go, that anybody can pick off the shelf and read about. I know what it is. I know what's inside of it. I know how to use it. So in a virtualization layer, a practical implementation, I think, takes it a step further. It's not just access to data, it's access to data products that kind of really makes this click.
And I think just adding on to that, let's transition into the next topic about, the role of data virtualization in a data mesh and in building those data products. So where have you seen that be successful, and how can you kind of build on and implement that?
I've seen over 100 different data mesh designs, and almost all of them, and I can only think of 2 examples that didn't need to use virtualization. So if I've seen 100, 98 of them are using virtualization. And the reason
pretty high percentage.
The reason for that is simple, right? The first rule of a data mesh is leverage the data where it sits. If you're building a data mesh and somebody says, great, let's move this data into a proprietary warehouse, you've failed the first principle, right? So the very first principle of data mesh is leverage the data where it sits. And so I could talk for another, I know we're short in time, so I'll leave the answer short, but I think that's, if you're building a real data mesh, you're leveraging the data where it sits.
Absolutely. And then the other architecture that we kind of dove into in the book, I didn't, Daniel did, dove into in the book was sort of this data lakehouse paradigm. Can you tell us a little bit about the outlook of data virtualization with the data lakehouse?
Sure, yeah, I would view the lakehouse as sort of one of the potential sources, data sources to the data virtualization platform. But again, the advantage of running over a lakehouse is lakehouse running over a lake. Yep. In the lake, the data is stored in usually open formats like Parquet files and so on that are faster to access. So just as data virtualization is good over any data lake data, it's also good over a data lake data as well. I think we'll keep it short since we're on time, but I think it's another source, and it's a very useful source for data virtualization.
Absolutely. I think I just have one last question. As you're implementing this data virtualization architecture, do either of you have any advice for the cloud era of practically implementing this data virtualization, the new era of data virtualization?
Yeah, I mean, agile, right? I mean, everything we do now is agile. What virtualization affords you the opportunity to do is deliver quickly. And so if you think it's going to take you 6 months to get there, you're thinking about it wrong, right? The idea is to be able to connect to the data sources and start to use that data quickly. The other practical, important piece of advice is to let the business do it with you, right? Don't go out there and build a virtualization layer with a bunch of IT teams. Go out there and actively engage your business teams. They understand the data, they know the data, become partners in that data, in that virtualization layer. And if I could add one more piece just on Lakehouse, what Lakehouse brings to the equation is performance. And so in a virtualization layer, it'd be fantastic if we could imagine connecting to any source and being able to perform really, really fast. The reality is sometimes we need to be able to access a source like a lake where you've got raw data, and in a lake with Starburst or in a lake with Iceberg, you have this perfect model of being able to take warehouse capabilities, if you need them for your applications, but also being able to take lake capabilities, if you need them for AI solutions or any other solution, all on the same platform. And you can do that incredibly fast. And so we used to think that speed required you to move data into one spot, and I think that's done. That nobody thinks that way anymore. I don't need a proprietary warehouse for speed. I can build it with virtualization, and I can get the speed with the lake house.
Let's give these two a big round of applause. And if anyone has any questions, I'd love to run the mic around if anyone has any questions to answer about data virtualization in the cloud era. Perfect. Let me pop down.
As long as all the questions are for you, I'm okay.
Hi, just wanted to understand that especially when it comes to compliance, like if some data is in Europe, some is in the US, it is spread across, then how exactly the data virtualization will work, right? That is one. And the second is that when you talked about that reading the data as part of the data mesh, reading the data from the source and executing it right there, right? Especially when the data warehouses or the databases are spread, like you have MySQL, there are Oracle databases, the speed, the response time, everything is very different across these databases as compared to a columnar DB and all that. So when you are seeing this problem as an analytics platform, then how do you ensure that the response time is consistent? How do you ensure that one query is not waiting for the other query to come in? And how do you eventually give that experience to the end user who is consuming that insight? So these are two separate questions.
Yeah, 4 separate questions, I would say.
Can I do a quick stab? Yeah. So let's talk offline also, just to give you the deeper, more technical answer. But I'll give you the quick, because that's a great question, right? From a data sovereignty, I deal with data sovereignty issues with a lot of different customers. It's one of my favorite problems to solve, because I had that problem when I was a CDO at an oil and gas company. The way that we're addressing that problem today is we're doing the compute in country, right? So India or Belgium or Turkey, whatever country, Europe is a bit different than Asia. China is a different animal. We'll talk about that separately. But I want to do the compute in country. And then in that country, when I build those data products, I make sure that the data product in that country is compliant with like a 1/1000 policy, or there's different policies every country has for the way data has to be aggregated before it's shared. I build data products in those countries. And then the only thing I share, Starburst has a capability called Stargate that allows me to firewall, if you will, what data products can be shared. So all my different countries and the instance on US soil can only see the data products that have been exposed to me through Stargate. That data product, it can be refreshed at a certain time frame and it can be cached. When I cache that data product or when I share that data product, I get incredible speed, right? Centrally, I can take those aggregated data sets and I can build new data products, derivative data products with better answers, and I can push those back out to the different instances or different countries. But I think the solution to that problem is data products, because they give me the compliance, they give me the ability to cache and get the performance. And there's a lot more to it, but I'll stop now because I've only given you 50 seconds to talk.
In 50 seconds, I'll try to do it. I can do it in the order you asked the questions. Your first question was dealing with data sovereignty issues. This is actually a great use case for data virtualization in general, because the whole premise of it is that you don't have to move data out of the source to query it. You leave it where it is, and the layer above it sort of pushes the work down. If you're using a push-based model, when you're using a pull-based model, you can sort of still divide the virtualization engine across different locations above the sources where they're located. So in general, when you have data sovereignty issues, data virtualization is one of the main drivers of modern data virtualization. The second question touched on the consistency and performance when running over MySQL and over Oracle and so on. So we're out of time, but I'll just answer what I can do really quickly. I mean, this is one issue, one age-old problems with this technology. It's very hard to get this right, and still today, we have data in MySQL or Oracle. The only way to get at it is through DDBC, and that is just or ODBC or these interfaces, which is going to be slow. And that's true back then, it's still true now. So when you do have data in those systems, you're not going to get consistent performance. It's going to be very much system dependent. There are tricks you can play though. So for example, Oracle, they support data partitioning. So what many of the modern data virtualization software does is that they sort of they leverage the fact that they know the data is partitions, and they issue separate sort of threads which draw data from different partitions in parallel separately. So they're able to rather than having one thread where you're sort of feeding data through one bottleneck to get to the tool, instead now have 5, 6, 10 different threads all getting data from different positions at the same time. And that's able to sort of improve performance. So we play those tricks in modern times, but it's still hard and it's still not perfect. It's not going to be perfect anytime soon.